computer. Cool. I think it's recording now. Hey, y'all. Sorry, I forgot to record the first like 10 minutes, so sorry about that. I've just been talking about nothing. But I was just talking about how project 2 is up. So if you want to take a look at the instructions, it's really just, you only need one data set this time. So there's no joining, there's none of that crap. It's a really good exercise for like if you have some data that's actually like you collected and you want to actually investigate relationships and do like tests, like hypothesis tests and things like that. So yeah, so it's the same idea. You'll be doing, talking about your data set, doing a MANOVA, kind of like you did for the homework, doing some kind of randomization test somewhere, right? Doing a linear regression, changing it up a bit, seeing if the bootstrap standard errors are any different, doing a logistic regression, and then finally doing some like regularization, cross-validation stuff, which we'll talk about at the very end. And that's really it. So we're kind of already, by the end of this week, we'll be pretty much halfway through it. Yeah, absolutely. So yeah, Santiago asked if you can use the same data set. So I think I say in here somewhere, yeah, it's perfectly fine to use either of the data sets from project 1 if they, meet these criteria. That's totally fine. But also feel free to, like, if you want to sort of branch out and do something totally different or whatever, that's fine too, right? Yeah, you'll be doing completely different stuff, right? So there won't be a lot of overlap. You can use the same data. That's totally fine. Let me move my head so I can find there's this. Okay. Oh yeah, and since I'm just started recording, for whatever reason, Zoom isn't letting me access the camera. So I've got this funny little workaround where I've got QuickTime pulled up, and it's not recording me. It's just sort of, spitting the video back out. So hopefully that's okay. Make sure to grab worksheet 14 for today. It's long. We won't get through everything today. I'll try to stop, last time I went a little over, so I'll try to keep it a bit shorter today, and then we can just finish up with what we don't cover on Wednesday. But yeah, take a look at that. It's on Canvas, and it should be also on the servers. Yeah, so the Lab 9 stuff will mostly be stuff from today. It's kind of just walking you through. The point of the lab this week, the main point is to see how ANOVA is regression. Like the two are sort of, ANOVA is a special case of regression where your predictor variables are categorical, right? And we're going to see that today, hopefully, if we get there. But the lab just kind of walks you through that. What else? I think that's probably okay. Can y'all see this all right? Is the screen big enough? I know it's like, this isn't the best situation. Hopefully that's okay. Yeah, just a few tweets. It's been a while for the tweets, so we can, this is an old tweet by Hadley, your esteemed textbook author. And notice, right, just spent 5 minutes staring at this code, trying to figure out what was wrong. And it's just that, right, you can see it's got to be this part because our studio is underlining it, right? Kind of like the spell check in Microsoft Word. And you can probably spot it, right? There's a period and it should be a comma. That's all it is. Like just forgetting commas or like accidentally putting a period or something instead of a comma, things like that. Here's another tweet. What programming tool or practice changed your life more than version control? And we're going to talk about version control for the third project. Kind of spoiler, the third project isn't exactly its own project, right? It's you don't have to do a lot of stuff for it. In fact, it's really just taking your previous 2 projects and getting them up on a really nice website that you make through our studio that you can customize if you want. But basically, it's just walking through my tutorial and like making a site, pushing it to GitHub, deploying it from GitHub, and then you have a site on the internet that's free, right? That you can basically show off your project for this course in. And that's kind of the idea. It's just like a living portfolio of the coding stuff you've done in case you want to show it off or put it on your resume or something. That'll be project 3, but don't worry about that for now. And this person chimes in and says, our studio and our markdown format changed my life by accelerating my productivity and ability to share data and analyses. And that's, that's a pretty solid testimonial. Uh, uh, so there's lots of inside jokes with our stuff. The deeper you could go down the rabbit hole. Um, Per is a package, a tidyverse package that's used to iterate for like you can use it for bootstrapping. Actually, that's what it's commonly used for. Um, it's got weird syntax though, and I've tended to avoid it in practice. And I like this. The man spread is man pivot wider. Anyway, yeah. So remember, I said like the main thrust of lab this week is like seeing that ANOVA is a special case of regression. This is a nice tweet, kind of right. Basically, every sort of test of means and stuff you've ever done, a t-test, ANOVA, a correlation, regression, they can all be thought of as like linear models, which I tend to just refer to as regressions. So they're all kind of the same thing under the hood. Today, you're going to see how a t-test is essentially a regression and an ANOVA is essentially a regression, hopefully, if we get that far. Cool. Oh, I didn't show, just in case. I can't remember if I had this stuff on here for like before I started recording. But if you have any questions for me, just holler at me. It should be recording now, I hope. Oh, one more. This is a nice picture. It's kind of showing like the way that I conceive of this course, right? We start out with like exploratory data analysis because that's the way that research works, right? Like you poke around, you try to see if there's an interesting relationship. I mean, you might come in with some hypotheses a priori, but like typically, you need to do some background research and figure out what, the literature says and what relationships there might be. And you just sort of look at like things like means and, correlations and stuff. And maybe once you have a hypothesis, you can fit a model, right? And try to predict something from something else. And then you can see how well your model's working, right? You'll do some cross-validation. You can check just to check to see how well your predictions actually line up with what you'd expect in the real world. Like if it was making predictions on new data. And then I can't remember what the last step is. I think if satisfied, just keep the model, right? But it's a nice little flow chart. And it kind of corresponds to the way we go through this course. Cool. I have a friend who works at Pixar, and this is my cool Pixar mug we got when we visited her. She's she's a graphics person at Pixar. And that's always what she wanted to be. Like even when she was like, because I used to do gymnastics with her when we were like in elementary school, and even back then she like wanted to work for Pixar. So it's like, or as soon as like Toy Story came out, right? There's this funny meme I saw with like about Zoom, and somebody like brewed a pot of coffee, but then poured a little bit of it into like 10 different types of drinking vessels, like a martini glass and a pint glass or different mugs or whatever. And then every time they took a drink, they would like alternate through the mugs just to confuse their students. I'm not that invested, but it's kind of a cute idea. It's been like rainy every time I've talked to y'all, or like overcast anyway. But if it's a nice day, maybe we should all like go outside and have like an outside class in spirit and sort of commune remotely with each other in nature. Okay, time to get a bit dry. So remember, right? Simple linear regression. You've got two variables, x and y, right? And you're modeling you're modeling y as a linear function of x, right? So you'd like to predict y values from some x value. You want to know the slope, right? So for every 1 unit increase in x, how much do you expect y to go up, right? And you want to know the intercept, right? So like when x is 0, what is y going to be? What do you predict y is going to be, right? But how do we get these coefficient estimates? These like beta 0 and beta 1, or like little b0 and little b1. Typically, if they're like this, right, if they're the betas, you can think of those as like the population parameters, but it doesn't matter, right? We're trying to estimate what these are, the true slope and the true intercept. And the way regression works, right, the way ordinary least squares regression works it tries to minimize the sum of the squared deviations from all of your data points to some line, right? So like, here's that car's data where you've got the distance it takes the car to stop and then the speed the car was traveling, right? And all these black points are just the point, like the scatter plot, right? So like this car right here was traveling like, I don't know, what is that? 14 miles an hour. And it took, and then when they applied the brakes and then they came to a stop in like 80 feet or whatever this is, right? That's that person. This car though was traveling at like 14 miles an hour. And when they applied the brake, it only took them like 60 feet to stop, right? So there's a little bit of, I mean, there's differences here. Like it's not a perfect relationship. Every time X equals 14, that doesn't mean Y equals the same thing, right? Your data is noisy. It's not a perfect, all those black dots don't fall onto a single line, right? This blue line here that we've drawn is the ordinary least squares best fitting line, right? It minimizes the distance of any of your data points to the line itself, right? And it's got some y-intercept and some slope. And notice it's a positive slope, right? When speed goes up, the stopping distance tends to go up, right? So cool. How do we find the slope and the intercept? Again, the slope of the line is the line that reduces these residuals. So the residual, right? The distance from your data point to the line itself, right? So these yellow lines, like if we look at this point right here, how far is that point from the line itself? Well, just take that point right there, its actual y coordinate, right? Which looks like it's about 30. Oh wait, 20, sorry, a little over 20. And then how far is it from this line, right? That's that yellow distance right there. But we need to know what this red dot is, right? We need to know when you plug in an x of whatever this is, like 7. No, wait, what is that? 6, 7, 8, 9, yeah, like 7-ish. So that'd be 7.5, right? When you plug in an x of like 7, what value do you get? What value does this equation spit out on that best fitting line, right? So we need to know what the slope and the intercept are in order to do that. How do we find the slope and the intercept? So remember from biostats, right? Think back. I know it's been a while. But you found the estimate for this guy, the true slope, right? You estimate that by taking the standard deviation of the y variable, distance in this case, over the standard deviation of the x-axis variable, speed in this case, times the correlation, right? Because correlation doesn't have any units. So we're basically just putting rise over run back into the correlation, right? We're taking the scale, like what's a standard deviation unit for y and what's a standard deviation unit for x, and we're putting that back into the correlation. And that gives you the slope, right? And then you can plug back in and find the intercept. But like, how? Like, where does that come from? Like, how could I, like, where do we get this? I want to walk through the derivation, like how to find the slope and the intercept and like where that comes from. So let me move myself a bit. So like I said in the beginning, this part wasn't recorded, but this gets a little bit mathy. So I'm going to take it slow. Don't sweat it. Like I'm not going to hold you like accountable for this stuff. I just want you to see it because again, I didn't really appreciate this until I had walked through this a couple times. So we'll be dealing with simple linear regression, right? One predictor variable, one response variable. We're actually going to assume that the y-intercept is 0 to start. And this is the same thing as assuming that your variables are standardized, like you've computed the z-score of x and z-score of y, right? Because remember, that best fitting line has to pass through the mean of x and the mean of y. But if you've done z-scores, the mean of x is 0 and the mean of y is 0. So if that line passes through the mean of x and the mean of y, it's passing through 0, right? And that's the origin, so your y-intercept is 0. When x is 0, y is 0. So anyway, don't sweat it. We're just going to assume we're working with standardized variables here. So here's our equation, right? So we're predicting y as 0 plus some slope times x, and then there's going to be some error, right? So that error is just that distance from the line to the point, right? So every true y value is some little distance, the residual, plus where whatever that red point is on the line. So if we go back, b times x, if the intercept was 0, would give us that red point on the line. And if you add back in that residual, then you get back up to the true value, right? So these estimates, these little y hats, those red dots, those are just like, if your intercept is 0, it's just the slope times the x value, right? So like if we want to get a predicted distance, we can take the speed the car was traveling times the slope, right? So we're just writing this out, right? All I'm doing is taking, basically it's this same equation up here, but we're assuming that the intercept is 0 to make it easier. And we can write a residual like this, right? So remember from biostats, residuals, how far is the actual data point's y value from the predicted y value? That's the same as saying, how far is this black dot from this red dot, right? This is your actual data point. This red dot is its predicted value for a given x, right? So when x is like 7, we predict the speed to be like 10, but it's actually like 20 for this particular car. Or I mean the distance, sorry. When the speed is like 7, we predict the distance to be, this line predicts it to be like 10, but it's actually like just over 20, right? So that difference between the predicted and the actual values is your residual. So we can write that like this, right? That's just your residual. That's just that error, that little distance. And every single y value, like every single data point has its own residual. How far is it from the line? How far is this other point from the line, right? So cool. So remember, we're after the value of b. We're trying to find the slope that minimizes those residuals, right? Because imagine if you did a flat line, like if you did a flat line through here, that would really suck, right? Like a lot of these residuals would be really huge. The yellow lines would be a lot bigger, right? This blue line going through here minimizes those yellow lines. We want to know what slope minimizes those yellow lines. So to do that, we can just write this out, right? So our goal is to minimize this thing, the sum of the squared residuals. So we're just going to take all of these little distances, square them, and add them up, right? These are residuals. We're going to take every yellow line, square it, add them up. And we know that we can write a residual like this, right? The distance from the data point itself to its predicted value. So the sum of the residual squared is equal to the sum of those little distances squared, right? Oops, geez, sorry. We also know y hat, right, the predicted value, we can write that as b times x. So this is just rewriting it as b times x. But here we have, you know, we have to FOIL because we got this thing squared, right? So do your first outer inner last. And then you end up with this quadratic equation, right? So this right here is the same as this right here. This is just the sum of the squared errors. It's a function of your data and the slope, right? So y is just the y data value, x is just the x data value. So that could be like distance, that's speed. The b is the slope. You're gonna know everything except b, right? You know what your data are. Like you have all your y values, you have all your x values. You're trying to find b such that this thing is as small as possible. What value of b results in the smallest sum of squared residuals? That's what regression is. It's just finding the slope that minimizes those squared residuals. Cool, let me move my head again. Neat. So we're trying to find b that does that, right? And we've got this function here. The reason I'm talking about this, it's really important to be able to, like, this is a really common sort of thing to do in statistics and machine learning. You have a function and you want to find a value that minimizes that function, right? Because usually it's like an error function. This is an error function, right? These are errors, like how far the data points are from the actual line, or like our predicted line. Those are errors. We're trying to minimize the error, right? So for example, here's the car data again, and I'm going to go ahead and make these z-scores. That way the intercept is 0, right? You can see this line passes through 0, 0, right? So I'm going to take car's speed, and I'm going to compute the z-score, so standardize it. I'm going to take the distance and standardize it, right? And then I'm just going to plot it, and I'm going to overlay the best fitting line, right? So you can say jump smooth. LM is the linear model method, right? So that's just a regression line. Our goal is to find what that slope is. And you can tell it's positive, and it actually looks pretty close to 1, right? So if you think about rise over run, if you start at 0, and then you go up 1, and then you go over 1, you're almost back to that line, right? So it's a little less than a slope of 1, right? If it was a slope of 1, you'd go up 1, go from 0 to 1 on the y-axis, and then you'd go from 0 to 1 on the x-axis too, right? So you go whoop, So the line would be passing through right there if it was a slope of 1. So you can eyeball it, but what is that value, right? How do we minimize this equation? Or how do we find b such that this sum is as small as possible? What value of b makes that sum the smallest? So cool. So first of all, let's distribute, right? So the sum of this thing, we can distribute this sum inside of there. So the sum of y squared minus 2b xy plus b squared x squared, right? We can distribute that sum in there and pull out the constants. So again, we're only summing up our data. 2b is a constant, b squared is a constant. So I'm just distributing the sum in there and pulling out the constants. This will make everything a bit easier in a second. This is the same thing though. This is just another way of writing the error. So what we can do is we can plot this. So let's actually plot this function right here. And let's use our actual data. So let's use that CARS data. So x and y is x is the standardized speed and y is the standardized stopping distance, right? So I'm just gonna plot a curve, and this is just a base R function that lets you plot a curve. So I'm gonna say, make a curve and sum up my y squared minus 2 times b times sum of x times y, right? So I'm just doing sum of y squared minus 2 times b times sum of x times y plus b squared times sum of x squared, right? So I'm just taking this equation and sticking it in right here, and I want to plot this. I want to plot the value of this function as I change b. So as I change the slope of that line, right, what value of b should I pick to get the minimum value of the sum of squared error, right? What value minimizes the sum of those squared residuals? This function right here that we just implemented in R, that is actually the error function, right? And you want that to be as small as possible. And hey, yeah, wouldn't you know it? It's a parabola, right? Because it's a quadratic function. Do you see what value of b this function would have the minimum value for? This function is lowest when it's in between 0.5 and 1, right? It's close to 1. Got a question about b being always positive. No, right? So it could be, imagine there was a negative relationship between your variables. Like maybe you're looking at, imagine this plot was just flipped to where as x went up, y went down. Then your slope would be negative, right? So you can have negative slopes too. It's totally fine. We'll do lots of practice. This is all totally just background of how to, the people who figured out how to do this stuff, how did they do it? Where do these numbers come from? So we want to find the b that minimizes this value. It looks like it's in here, right? It's going to be close to 1, maybe a little less than 1. But to find the precise thing, we can use calculus. So this is a good example of everybody takes calculus and then people don't really use it in practice. It's really good at finding minimum values of functions, what value of b results in the minimum value for this function. Calculus is great at that, right? Minimization stuff and optimization stuff. So what we're going to do is this function right here, right? Remember from calculus, I know it's probably been a while. If you take the derivative of this function, that gives you a new function that spits out the slope of the line tangent to this function, right? When this thing is at a minimum, what is the slope of the tangent line going to be? Cool, 0. Yeah, the slope is going to be 0, right? It's going to be perfectly flat when this thing is at a minimum. If you're at the bottom of a curve, right? Like you can imagine, I wish I could draw on the board. You can imagine the slope, once you get about right here, the line tangent to that point is totally flat, right? So all we need to do is take the derivative of this function right here with respect to b, right? Because everything else is a constant. That's just data squared, that's just data with respect to b, and then set it equal to 0 and find what that b is that makes that slope equal to 0. And remember, so it's the sum of the squared residuals. So this value will always be positive, right? It doesn't matter if the residual is up or down, squaring them makes them all positive. So yeah, cool. So let's do this. So we've got this thing distributed. We're trying to minimize the error here, right? The sum of the squared error. We're trying to find B such that this is minimized. And you typically see it written like this, right? So we need to take the derivative with respect to B. So let's do that. So take the derivative. The derivative of this thing with respect to B is 0, right? Since there's no B in there. The derivative of this thing with respect to B is just 2 times the sum of x, y, right? Because B is just right there, right? And then the derivative of this term with respect to B, we'll just bring that exponent down. So 2 times B minus 1, right? So that's 2B plus x squared, right? So it's actually a pretty easy derivative. This is the function that gives you the slope of the tangent lines. Now we just have to set it equal to 0. So we take the derivative of that function, set it equal to 0, and then solve for what B is, right? What value of B makes that slope equal to 0? What value of B minimizes that function? And it's cool if you do this, right? So just take this thing, so -2 times the sum of x times y plus 2b times the sum of x squared. Take that and set it equal to 0, rearrange and solve for b. When you do that, yeah, you find that b is equal to the sum of your data points x times data points y over the sum of the x squared, right? And this is going to be your b. This is your slope. That's it. And you can actually you can show that this is the case, right? So the slope of the best fitting line you can find by taking all your observations, multiplying them together, x and y, right? So multiply every distance by speed for all your values, add those up, and divide it by the sum of all your x's squared. So square all your x values, square all your speeds, and add those up. When you do that, you'll get your slope, the slope of that line. You can do this in R, right? So you can just say, hey, multiply my distance times my speed, sum them up, divide by my speed squared, right? And that's the slope. The slope is 0.8. Remember, it was close to 1, but a little bit less. This is the slope of the best fitting line. And it's really cool. Like we just found what oh crap, sorry, it's lagging. We just found where that would be tangent to with a slope of 0, right? A B would be like 0.8-ish, so right in there. And you can actually see that this corresponds, right? So in R, when you can just run a regression like this. You can say linear model regress y on x, right? So y is my response variable, x is my predictor variable, right? And cool. And you can see that it's the same value, 0.8069, right? Or 8069 times 10 to the -1. So just move that decimal back 1.8069. Same thing we get when we do this, 0.8069. Neat, right? And again, we're forcing this to be 0. This is 0. It's a way a computer says 0. The intercept is 0. The slope is exactly what we found right here. So that's really cool. It's just a function of your data, right? X times y, sum it up over x squared. Bless you. Oh, it's weird. So did y'all hear, sorry to completely, this seems like a good break. Did y'all hear that animals are contracting coronavirus? Like there's some tigers at the Bronx Zoo that are coughing and stuff, and like they've isolated, and it's like, it's coronavirus. Have y'all heard about that? It's bonkers, right? And my cat's been sneezing a lot, and it's freaking me out. It really is. I don't know if you can see. Where is she? She's over there in the plant. She's been sneezing. Yeah, I don't know what. I mean, we don't have it, right? Like we haven't gone anywhere, and we're totally asymptomatic. So like, but it's still really weird. Sorry, y'all. I unplugged everything when I moved the computer. Yeah, I've been having to say bless you to that cat a lot. She's been sneezing. It's been really weird. She woke me up in the middle of the night having a sneezing fit. Cat sneezing, it's bizarre. Anyway, strange stuff. I don't know what to think about that. Weird development. I wasn't expecting it to, be a cross-species thing. Anyway, still sneezing. Okay, sorry for the aside. Although maybe it's good. Maybe it's good for me to shut up every now and then. And so cool. This is our estimator, right? This is the slope that minimizes the residuals, right? This results in the best fitting line in a simple linear regression where the intercept is 0. Now take a look at it, right? So if you think about it, the top part looks kind of like a covariance, right? So the covariance would be x minus the mean of x times y minus the mean of y divided by n minus 1. And a variance would be x squared minus the mean of x, I'm sorry, x minus the mean of x quantity squared over n minus 1, right? So this looks pretty similar. So you can write it like this, right? So that's the formula for a covariance. That's the formula for a variance. And if you simplify them, if you have the covariance of x and y over the variance of x, that simplifies to this right here. So sum of x minus its mean times y minus its mean, right? To take every distance of x from its mean and y minus its mean, multiply them together, add them up. And then for the variance, take every distance of x minus its mean, square it, and add them up, right? Look at how similar that is. Sorry. In fact, it's like the same thing, right? Like, except for we're just not scaling it explicitly here. We're not doing x minus the mean, y minus the mean. We're just doing x times y and x squared. So cool, right? So if this is scaling it for us, and this is the equation we use to find the slope when we've already scaled our data, this right here should give us the slope if we don't scale, like if we don't scale our data. The true, like for any data, like don't scale it, just leave it alone. This right here, putting the covariance of x and y over the variance of x will give you the slope of predicting y from x, which is really, really cool. So just to show you this, right? So if we look at the CARS data set, if we do the correlation of speed and distance, right? 0.8069, that's the same as that slope, right? Remember our slope from before? 0.8069, this thing. So this thing is actually giving you the correlation if your data is already standardized, right? Here's how you would do a full regression in R, like without standardizing. So if you actually want to know, hey, I want to predict distance from speed, but I want it to be in terms of the original units, right? I don't want to have to go up a standard deviation in this one and go up a standard deviation in this one. I want to know, like, for every one. So first of all, let me back up a bit. I feel like interpreting this, right? So basically we know the slope is 0. I'm sorry, the intercept is 0 and the slope is like 0.08. Basically 0.8, basically 0.8, right? This is telling us for every one standard deviation you go up in speed, you go up 0.8 standard deviations in stopping distance on average, right? And we can see, are those standardized? Yeah, this is x and y standardized. So for every 1 unit increase you go up in speed, right, then you expect to go up 0.8, right, 0.8 units, standard deviations, because these are standardized, right? So each unit is a standard deviation. So go up 1 standard deviation of x, we go up 0.8 standard deviations of y, right? That's the slope if you've standardized your data. That's the same as the correlation, right? If your variables are standardized, the slope and the correlation are the same. But typically you don't want them to be, like, you don't want to mess, you want to keep your data in its original form, right? You want to be able to say, like, for every 1 mile per hour I go up in speed, how much does my stopping distance increase, right? Not standard deviations. So this is how you find that in R, right? Remember the syntax from biostats. So we're predicting the car's distance from its speed, right? And you can do this. You can say data is cars, predicts the distance from the speed. It's always y tilde x, right? And this will give you the intercept and the slope of the best fitting line, predicting distance from speed. And notice, these aren't scaled. These are just your regular old data. So even though a 1 standard deviation increase in speed corresponds to a 0.8 standard deviation increase in distance, that's the same thing as saying a 1 mile per hour increase in speed leads to a 3.9 feet, I think it's feet because they're imperial, 3.9 feet extra stopping distance on average, right? And you can find the same slope like this. You can take the covariance of x and y, divide by the variance of x. This is a general estimator for the slope here. And that's why that number and that number are the same, right? This is what R is doing under the hood when you run that regression. And again, I know this is like a lot of extra details, and it's been a while since you've seen this stuff. I wasn't satisfied with, like, I've taken, like 3 or 4 classes about specifically like regression stuff. And the first couple I took, they never showed me like where these numbers come from. They're just kind of like, oh, you run the code and it spits out the slope. And it's like, it didn't really start to make sense until I had really worked through a few examples of like how to derive them and like, oh yeah, this makes sense. But again, I know it's been a while, and I just wanted to show you this. So cool. So this picture here is kind of like that ANOVA picture, right? It's sort of like, I mean, it really is kind of the same thing. So we've already seen this picture over here, this one on the right-hand side, the error sum of squares. So that, to get the sum of squares error, how far is each of your y values, right? Each of these, like this one's 80, right? How far is it from the predicted value, that red dot, squared and added up? That's your sum of squares error. That's the thing you minimize, right? You're trying to find the slope of that line to make that as small as possible. Then you have your total sum of squares, right? So your total sum of squares is actually, this is what it would look like if you just use a flat line to predict. So let's say you didn't take speed into account at all. Like, look at this plot over here on the left-hand side, right? This would be a really dumb line to choose, right? It's really flat, and it's not making good predictions. Basically, it makes the same predicted y no matter what x you choose. So like a speed of 20, you'd predict a y equal to the mean of y, right? A speed of 10, you'd predict a y equal to the mean of y. If you do that, that sucks, right? And these yellow lines are showing you how much it sucks. If you square these and add them up, that's very big, right? That'd be much bigger than these little yellow lines squared and added up. The distance of each data point's y value from the mean of y, right, which is what this line is at, that's just the mean of y right there, which is like 40 something. What is that like? That's 60, it's probably like 44 or something. How far is each data point from the mean of y, right? If you take those little distances, square them, add them up, that's your total sum of squares. That's like all the variability in your, in y. It's basically just the standard deviation of y, but without the denominator and squared, right? It's like if you multiplied the variance by n-1, you'd just get the numerator, which is this, right? How far is y from the mean for all these data points squared and added up? So that's your total variability. You can break that into this error part, the leftover noise around the line, right? But then this is the money shot right here. How much better are we doing by using the slanted line, the one that actually has a positive slope, versus using this flat line, which really sucks at predicting, right? It makes the same prediction every time. Well, this slanted line, right? These little yellow lines are showing you how much better you're doing, right? So the distance from the mean of y, which is this blue line, like 44, to the predicted values, these red dots, that's your regression sum of squares. And that's like, if you take those little yellow distances, square them, add them up, that's how much better you're doing by using the regression line instead of using a flat line, right? A flat line would just be, I'm not using x at all to make predictions. I'm saying the mean of y every time. Cool, and if you add up, like take a look at, where's a good data point to look at? If we look at, yeah, we can look at like, yeah, we can look at like this big one, I guess. Is that a good one to look at? It doesn't really matter. So if we focus on this point way up here, right? This car was traveling really fast and it had a really high stopping distance, right? I mean, it took a long time for it to stop. The regression line predicted it would only take that stopping distance, but it took it all the way to 120 to stop, right? The regression line predicts like 80. So here's how much better you're doing using the regression line instead of using this flat line. The flat line would predict 44, right? So that little bit tells you how much better you're doing using the regression line. And then here's the error for that data point, that big yellow line right there, all the way to the red. Because you can see we're not getting close at all. We're way under predicting that point, right? On average, we're making pretty good predictions, but for this point in particular, we're sucking, right? We're predicting this red dot for the y value when its actual y value was 120, right? So what's really neat about this is you can take that total variability, break it into the part explained by the regression line, and then the error, the leftover noise, like the stuff you can't explain by the regression line. So it's really similar to sort of the ANOVA way of thinking about it, right? You take the total variability, you break it into how much you can explain with the line, right, versus not using it, and then how much is left over, how much noise is there around your line. And you can imagine, right? Like imagine there wasn't nearly as good of a relationship between speed and distance. Imagine it was just a like static, like cloud of points. There'd be a lot more noise, right? And then this line wouldn't be nearly as steep if it was just a staticky, you know, if it was just a scatter shot, like you know, like if this was all just, if there wasn't like as clear of a linear trend. So this picture is like everything, right? It's you want this to be big, right? The bigger this is, the better your line is doing at predicting, right? The better it's doing than just using the mean of y, because the mean of y would be a really crappy predictor. Why would we just predict the mean of y if we can take x into account, right? Because x obviously has some bearing on what y is. When x goes up, y tends to go up. It'd be silly just to use that horizontal line, right? Using this line gets us much better predictions. It cuts down that error. Like imagine if this is your total error, like for this data point, look at this data point, right? Look at this guy who's going 25. That's your total error if you use just the mean of y, right? Look at how much of that error you cut off. So this is how much you save by using this line to predict instead of using this line to predict. All of that is stuff you save, right? So that's how much of that error you're actually explaining with that line. And notice you're doing a pretty good job of predicting that one. So the car going 25, we were predicting it would take 80 feet for it to stop. And it actually took like 85 feet for it to stop. So we're doing a pretty good job with that one, right? The residual is tiny. It's very small, only like 5 feet. So we're predicting that one pretty well, right? This just shows you how much better you're doing with the slope, right? With the best fitting line, rather than using the mean of y, which is, I mean, if you didn't know x, that'd be the best guess, right? If you had no idea what the car's speed was and someone said, hey, how fast or how long do you, or how far do you think the car took to stop, right? What do you think that distance was? If you didn't know x, your best guess would just be, oh, I don't know, the mean of y, the mean of all the stopping distances, right? But if you know x, you can make better predictions than that, right? It's like, oh, if I knew the car was going 25, I'm going to predict it took 80 and I'm going to get really close. Whereas if I don't know the car is going 25, I'm going to predict 44, and that's going to be wicked far from the actual car stopping distance, right? So it's all about how much better you're doing with a line with a slope versus a flat line, right? And that's your sum of squares regression. You want that to be big. You want this sucker to be big, and you want this sucker to be small. Just like with ANOVAs, right? You want the sum of squares between to be big, the sum of squares within to be small. With regression, you want the sum of squares regression to be big and the sum of squares error to be small. It's the same idea though, right? Partitioning the total variability into two different pieces, a signal and some noise, and seeing if there's, there's still a relationship at the end of the day. Like seeing if the signal is big enough to warrant saying, yeah, I think there is an actual positive relationship between these variables. So remember R squared. It sort of tells you about the strength of that relationship. And in biostats, I talk about this a little bit. I'm not sure if other instructors go into it. But you can calculate R squared, right? Just using these quantities right here. The proportion of variation you would explain with X, right? That's just the sum of squares regression out of the sum of squares total. So out of all my total variability, how much of it can I account for using speed, right? How much of it can I account for just by knowing speed and using this best fitting line? So I take my sum of squares regression out of my sum of squares total. That's your R squared. That's all it is, the proportion you can explain. This middle one is how much you can explain. This right one is how much is left over, right? You can't explain. And then this left one is the total variation. So total variation equals the part you can explain plus the part you can't explain, the leftover noise, right? There's always going to be noise. But the R squared is just, if you take these yellow lines, sum them, take these yellow lines, square them, and sum them up out of these yellow lines squared and summed up. Or you can do 1 minus the sum of squares error out of the sum of squares total, right? Because if this equals this plus this, then 1 minus the sum of squares error, or sum of squares total minus sum of squares error equals sum of squares regression, right? You can rearrange these. It's like saying 5 equals 2 plus 3, 3 equals 5 minus 2. Like you can rearrange this however you want. That's all it is. So we can compute these, right? So take a look at this. Let's actually compute. So cars dist, when you run cars dist in R, so I'd encourage you to like actually run these, right? So, I mean, can I like bring this down? Nuts. I don't think it's gonna work. Let me just hop on a server. Is this a server? Yeah. Let me go away. Cars dist, right? Now crud. Sweet. Let me make this bigger. Bigger. These are just the stopping distances of the cars, right? So if I say cars dist minus mean cars dist, these are the distances of, these are those little yellow lines from each, like, where's my, let me actually move this over here. I think I can go back and forth now. These little yellow lines, how far is each stopping distance from the mean stopping distance? That's what these numbers are, right? So if you take these numbers now and you can pipe them into, wow, let's not do that. Let's take these distances, square them, and then sum them up. So you can pipe that into sum if you want. Whoa, pretty big. The sum of squares, oops. The sum of squares total is that, right? How far is each stopping distance from the mean stopping distance squared and added up? And this should be actually equal to, if you say variance of cars dist times 50 minus 1, so times 49. Yeah, that's the same value, right? Because this is just the numerator of a variance. So anyway, that's your total variability, right? So remember before fit, so I think you ran, is it fit one? Crap. So fit one, let's just do LM. We want to predict stopping distance from speed, right? And we want to use data equals cars. And then summary fit one. So this is our regression, right? And there's the slope from before, the intercept. This is just your regression output. I wanted to go ahead and save this fit one though. So let me rerun that. Cool, that's your total sum of squares, right? What's your regression sum of squares? So remember again, that's how far each, if we flip back over, how far is each predicted value, these red dots, like where they fall on the line from the mean of y, right? Because the mean of y is just this line. It's going to be 44 or whatever every time. So the mean of y is just the mean of the distance. So mean, oops, sorry. Mean cars dist. Oh, it's not 44, it's 43. That's the average distance, right? So how far is that from the predicted values? How do we get the predicted values? It's actually kind of nice. You can just say, summary fit one, and then do $ fitted values. So if I do this, oops, didn't like it. Names fit one. Fitted values. Oh, I don't even need summary, sorry. I need fit one, $ fitted values. These are the predicted values. So for car number one, we would predict its stopping distance actually to be negative, which is weird. But if we go back and look, oh yeah, this one is being predicted negative, right? That red dot is below 0. So car one, it's predicting a negative stopping distance, which is pretty stupid, right? Why would you predict a negative stopping distance? But it's the best fitting line. So cool, so how far are all these predictions, right? Those are just the red dots. How far are those from the mean of y? So if you take those minus mean of, what is it? Cars dist, and you're gonna square them and add them up, right? So sum those squared, but wait, we wanna square them first. So square those and sum them up. Cool. So this is your regression sum of squares. How far away are the fitted values? How far away are the predicted values on the line from the mean of y, squared and added up, right? And if you do, so I should just save these, right? I'll save this as sum of squares regression, sum of squares total. I'll save as this thing. So sum of squares total is this, sum of squares regression is this. So that means your R squared should be what? Sum of squares regression over sum of squares, oops, sum of squares total. So it's 0.65. That isn't bad. And remember, you can compute the R squared just by squaring the correlation coefficients. You can say core of cars, dist, cars, speed. If we square that, that should be R squared, and it is, right? It's the same exact value. So again, this is just, it's kind of extra. It's not a, it's just showing you break down that total sum of squares into the sum of squares regression, and then the sum of squares error is just sum of squares total minus sum of squares regression, right? And that's this number right here. You can compute that if you want. Take every value of y, so cars dist, every stopping distance. How far is it from the fitted values? So fit one, fitted values. Take those and square them, and then sum them up. Oops, sorry. I shouldn't do it this way. That's a bad way to do it. Let me, I'm not practicing good. Take those distances. So that should be squared, sum them up. Cool, and that's the same thing you get. So the sum of the car stopping distances from the line, right? So how much noise is there? How badly are we doing? Like, we predict it's going to be this, but the actual car stopping distance was this. If we do that for every car, find the distance, find the error, square them and add them up, that's what we get, right? And that's the same as sum of squares total minus sum of squares regression. So these are just, you know, just relationships that are really, I mean, if you understand, like once this starts to sink in, then you understand everything about regression. This is it. This is like, you know, under the hood, this is what's going on. So you can compute these things. And this is the proportion of the variance that's explained by speed. So how much of this total variability in stopping distance is due to the speed of the car? 65%. That's what R squared is telling you, right? How much of the total variability is due to the predictor variable. In this case, it's speed, right? So R squared, that's all it is. Variation explained out of the total, right? What proportion of the total variation can we account for? Total variation in stopping distance can we account for just by knowing the speed of the car? 65% is pretty good. It doesn't sound good, but it's pretty good. Just by knowing the speed of the car, you can explain 65% of the variability in how long it takes a car to stop. And these are cars in the 1920s, right? So they're not going very fast, and they probably have weird brakes and stuff. I don't know what a car looks like in the 1920s, but it probably doesn't look very good. Cool. And you can also just straight up grab the R squared from the model you fit. You can be like, hey, give me that R squared, and it'll give it to you. You can also compute it by hand if you want. Cool. So that's R squared. And you can just square the correlation coefficient. That's fine. Whoa, we're already, geez. Oh man, running behind. So anyway, like this is a lot of background stuff, and I've still got more background stuff for you before we get into like actually applying this stuff in practice. But that's simple linear regression, right? In a nutshell, it boils down to this right here. We're predicting one variable from another variable. What's the best fitting line through that cloud of points? And then we can do things like quantify how much better it is to use this best fitting line than it is to use just the mean of y or some other flat line or something. And that ends up being an important way to quantify how good your model fits, right? This fits pretty good. How well does it fit? Well, the R squared is 0.65, so that's decent. And you can see there's still noise, right? If these points were tighter, if it was like a nice little cloud right around that line, then it would be a smaller R squared, right? The fit would be better. There'd be less noise. Cool. Yeah, so I know like a lot of background stuff, but at the end of the day, we're just trying to predict one variable from another. It's kind of like y equals mx plus b uh, on steroids. Um, this one really y equals mx plus b on steroids. So once you get into multiple regression, right? So we're adding multiple predictor variables. We're trying to model some variable y as a function of a few other variables, right? But more than one. So far we've just been considering this sucker, right? Where we've got an intercept, a slope, and one variable. But maybe we want to look at the contribution of other variables, right? So maybe we want to know about like predicting someone's blood glucose from their BMI and their age and their whatever, right? Like all these other variables. We'll be doing a lot of examples with this medical data set, just because it's a handy data set. But this is sort of the model, right? You're modeling some y as a function of all these other variables. You're assuming that this relationship actually exists in the population. And it'll tell you, right? Each of these little slope estimates you get will tell you the extent to which your predictor variables or your explanatory variables, these x's, are associated with y. Cool. So when you look at this, right? So this is the true model. We're going to try to estimate this, but we're assuming that like these are the true values, right? So when you set x1 equal to 0 and x2 equal to 0, right? So let's say you're predicting blood glucose for someone with 0 BMI, who has 0 age, who has 0, you know, whatever. When you do that, these all drop out, right? All these terms disappear and you're left with the intercept, right? So the intercept is always the true value of y when all your other variables equal 0, right? When all of your predictors are equal to 0. For each of these little slopes, right, is telling you how much do we expect y to increase for every 1 unit increase in like the variable x1, so maybe like BMI, holding these other things constant, so not changing them. So if we have a fixed age and a fixed whatever, right, how much do we expect y to go up for every 1 unit increase in BMI? Does glucose go up with BMI? That's what this slope would tell us, right? On average, we expect y to go up B1 units, holding everything else constant. So this is really rad, right? This is super general. You can stick all kinds of stuff in here. You can do interactions. You can do like, you can model things as like, you know, not just linear. You can put quadratics and things in here, all kinds of stuff. So this is what we get, right? We get a model that predicts, maybe you want to predict, like you get these estimates. You get an estimated intercept, estimated slope for x1, estimated slope for x2, up to ever how many variables you have, right? And when you do that, when you take your intercept plus this times x1 plus this times x2, it just spits out a single number, and that's just the predicted value for y, right? So maybe like car stopping distance plus the car's tire tread plus, you know, other variables about the car. What's the predicted stopping distance? Oh, sorry, I should have said speed. Car speed, car tire tread. You can factor in all these other things to get a predicted stopping distance, right? And these are just your estimates, just like the, you know, little b0, little b1 that we estimated in biostats, or, you know, a few minutes ago. And just like before, right, they give you the best fitting predictions. It's no longer a line though, right? A line is just two variables. This is actually like a plane. We'll see that in just a second. It's actually really important to see it as a plane, and I'll talk about why in just a second. But like if we're interpreting little b1 right here, right? So that'll be a number you'll get. When you run your regression, it'll say like, here's your intercept, here's your slope for speed, here's your slope for tire tread, here's your slope for, you know, gas mileage or whatever. And little b1 will tell you, right, how much we expect stopping distance to go up when you go up 1 unit in speed, controlling for everything else. So holding everything else constant. And this idea of controlling is going to come up over and over and over again. And it's a really kind of a elusive concept, but we're going to like, it's super important to like see what it actually means. So I'm going to try to explain it in a couple different ways, because it didn't click for me for the longest time. Like I probably had a full class in regression stuff before I really understood what controlling meant. So I'm going to try to kind of give you some motivation for that. So real quick, this will probably take a bit. This is just for the, if you're really interested in the math stuff, we can derive these ones too. Problem is, we've got a lot of variables now. Before we just had two, right? We had X and Y, and we, you know, we found the error function, we minimized it, we found the slope that minimized it, right? And we were done. It's pretty much the same story here, but we have to use linear algebra to do it. So just real quick, right? And again, this is just totally extra stuff. I just want you to see this because again, it didn't make sense until I saw it. We can write this as like matrices, right? So these are your response variables. So maybe this is stopping distance for car one, stopping distance for car two. Maybe this is the speed car one was going, the speed car two was going. Maybe this is tire tread for car one, tire tread for car two. And you want to look at the impact of both of those things on stopping distance, right? So you can formulate this with matrices, right? You always have a column of ones first because the intercept doesn't change y as a function of x, right? It's always the same. It doesn't change as a function of x. So you put ones there, and then you put your data. And this is just the model, right? If you multiply 1 times b1 plus speed for car one times the slope plus tread for car one times the slope, right? You end up this is just a more concise way of writing all this stuff out. It's the same equation as before. It's just in matrix math. And again, you don't need to know this. I just want you to see it. Well, you kind of do. You won't need to derive it yourself, but you'll need to see the endpoint. So this right here, E transpose E is it's just a way of writing the sum of the squared error, right? Imagine if you take this and put it on its side, and then you leave one up and down like this, and you multiply them together, right? That's going to sum them up. So just to show you that, right? Imagine, so these are, the errors are, let's say fit 1. What are the residuals? Residuals are your little distances, right? If you take this and make them a matrix, here they are, right? This is just a column of numbers. Let's make it more manageable. I'll just take, let's do it like that. So if it's a matrix, I'll just call it, I'll call it E for now. So if you do E, if you do transpose E, matrix product E, hey, look, it's the same thing as, remember this number? That's the same as your sum of squares error, right? It's the same as doing each error times, like each error squared and added up. It's just another way of writing it, right? It's just a matrix way of writing it. And it just makes the calculation a bit simpler. So this is just the sum of squared error, right? And this is just the matrix way of writing that out. So y minus the predicted value of y. The predicted value of y is just this matrix times this matrix. And we can distribute and rearrange things and take the derivative with respect to b. And you can do, if you haven't done calculus with matrices, it's really the same thing. So watch, right? If we take the derivative of this thing, this term drops out because that's like y squared. This is just b times that thing, right? Because 2b, I'm sorry, no, this is 2 times that thing because b goes away, right? Derivative of this term, b drops out. And then this one has 2 b's in it. So that's like b squared. So 2 times b times x squared. So it should look pretty similar to the other one, just in terms of matrices, right? Like before we had 2 times the sum of xy plus, I'm sorry, negative 2 times the sum of xy plus 2b times the sum of x squared, right? This is just writing that with matrices. These computations this does the same thing as doing sum of x times y. This does the same thing as doing sum of x squared, right? And then we can set it equal to 0 and solve for b. And this right here, so setting it equal to 0, right? And just rearranging, solving for b. To get b by itself, right, you have to take the inverse. You have to get this away. So multiply by the inverse on both sides. Don't worry too much about the derivation, but do this thing right here is a very magic little equation. You take this is your x matrix, right? This thing right here with all your x values. You take that times its own transpose. So x transpose times x, take the inverse of it, and then multiply x transpose times y, right? So this should look a lot like, so remember from before, estimating just a single slope in simple linear regression was the sum of x times y over the sum of x squared, right? And remember how we thought of like inverse as dividing. So this is like dividing by the sum of x squared, and this is like the sum of x times y. So it's really the same thing, it's just in matrix formulation. It's just like doing sum of x times y over sum of x squared. You can kind of see, right? It's similar. Sum of x times y. I mean, it's identical. It's just the matrix formulation. So just to make this concrete, let's test this to make sure it works. Imagine your data are simple like this. You've got 10, 13, and 14 for your response variable. And then for your predictor variable, you've got 2, 5, and 12, right? So you can put your data into matrices like this. So here's your response data. That's the outcome, right? And then here's just ones for the intercept, and then 2, 5, and 12 for the predictor. And we want to know what those B0, B1 are. We want to know what those estimates are, right? What's the slope and the intercept for the best fitting line through these 3 data points? And these will just be your residuals, right? So here's what's really rad about this. We can try it. So take this matrix transpose times itself, right? So we can actually go ahead and make these 2 matrices. So I think you have the code, right? You can make these 2 matrices. Let me up on the server. And again, this is just something that I thought was so beautiful when I first saw it, but I didn't see it until like grad school. And I should have seen it much earlier. So here's y, oops, sorry, here's y, here's x, right? If you do transpose x times x, right? And then we're gonna solve that. So that's the inverse of x times x. So that's that right there. If you do that times x, I'm sorry, transpose x times y, you end up with this number right here and this number right here. Those are your little b0 and little b1 that minimize the sum of the squared residuals. This is the equation for the line. That's your slope, that's your intercept. And you can sort of prove it to yourself. You can say, okay, let's see, is that actually true? So we'll do y by, and we just want this column, right? So we want these numbers by these numbers. So y by big X, I'll just say y by 2, 5, 12. And look, that's what it's giving you. That's the intercept. The intercept is 10, and the slope is 0.35. I know this looks crazy, right? It looks bonkers, but it's actually a really elegant thing, right? And it's exactly the same. So take a minute and stare at it until you can see that this is the sum of x times y over the sum of x squared. It's just like that, except with in matrices. Remember how the inverse is like dividing by, right? It's not exactly the same thing, but it's analogous, right? And it works like a charm. And you can stick ever how many columns you want in there. This thing is magic. So in lab, you'll have to run it, but you won't really need to talk much about it at all. I just want you to like actually run it and see what it's doing. But it's giving you these estimates. So the slope and the intercept for the best fitting line. So just to prove to you, right, you can do it. So let's do cars dist. Let's set that equal to y. And then cars speed, let's set that equal to x, right? And if you make your matrices again, so maybe you want y, so x is gonna have to be, let's do, it's kind of annoying. We'll do x equals matrix. We want to repeat 1 50 times, right? Because we want 50 ones in the first column. There's 50 variables. And then we just want to put x in there. And we want in row, let's do in col. We want there to be 2 columns. So what does x look like? Yeah, that's what we want x to look like. So there's our data, right? If we rerun this equation, hey, that's the same thing as doing your initial regression, right? Remember when we did LM dist by speed data equals cars? Same numbers, right? Intercept, intercept, slope, slope. So that's where they come from, right? I mean, and you're just minimizing a function that's a bit more complicated. It's the same thing, right? So I just wanted you to see, like, under the hood, what these things are all about. Again, don't sweat it. I know this is crazy, and I know you probably haven't seen, unless you've had multivariate calculus, you haven't seen like matrices you know, taking the derivatives of matrices and stuff. But don't sweat it. I just want you to, this thing right here is most of statistics that everyone does boils down to this thing right here, and they don't know it. Like, so you're kind of in on a little secret that everything is just this right here. But I still have to show you that, right? So we still have to kind of see how everything's a special case of regression. And we've been dealing with the nitty gritty and not like actually applying it. So let's apply it real quick. Oh, I just wanted to show you, right? Remember in biostats, you found your slope by doing the correlation times standard deviation of y over standard deviation of x, right? If you do it that way, you get the same slope, right? You can ask R to give you it. It'll give you the same slope in the intercept like we just saw. But this way is really cool because you don't have to, like, it's all your data, right? Anyway, I know I went through that kind of fast. Don't worry about it. I won't quiz you over it. You will need to at least run this thing one time though, because I want you to actually take the time to see how beautiful it is. That's a lot of background and a lot of like nitty gritty stuff and a lot of symbols. So again, don't sweat it, but let's actually practice this real quick. I know we don't have a ton of time. So here's this data set I want to play with. You may have already been looking at it. So go ahead and grab it from my site. That's probably the easiest place. It's just mysite.com. I think this code is in the worksheet, right? So just use worksheet 14, run this code. And I'm just going to do some quick like cleaning, kind of stuff like y'all did for your project. Some of you had to clean up. Some of you had to do some extensive cleaning, which was, you know, that's right. But anyway, cool. So here's this data, right? We've got the patient ID, the patient age, patient gender, diabetic status, edema, cholesterol, blood glucose, blood platelet count. I'm sorry, no, this is blood pressure. I thought there was a platelet. Oh, there it is. There's platelet count. And then BMI. So that's, you know, it's just some variables, but you can ask like, hey, can we predict, how well can we predict someone's BMI if we know their cholesterol, right? Or whatever it is. That's the whole point of doing this, trying to find a model that lets you predict one variable from the other variables, and how well can you predict them, and all those kinds of questions. Cool. So for example, we can look at the relationship between blood pressure and BMI, right? So maybe we want to predict someone's blood pressure, and all the information we have is their BMI. Is there a significant relationship between BMI and blood pressure, right? You can just make a quick plot. You can kind of eyeball this, right? And it's like, yeah, you know, it looks like there's a positive association. It's not super tight, so your R squared is going to be small, but like, you know, it's probably a significant, like the slope of the line going through these points is probably non-zero, right? So think back to biostats, right? The null hypothesis is that BMI doesn't explain any variation in blood pressure. And remember, you can partition the total variation in blood pressure to the part you can explain with BMI and the part without, right? So you could do that by hand if you wanted. Then the alternative is BMI does explain some variation in blood pressure, or the true slope is not zero, right? And also going back to biostats, all your test statistic is just your estimated slope divided by its standard error, and that follows a t-distribution, right? With n minus 2 degrees of freedom, where n is just the number of observations in your data set. So you can run this regression in R, right? Piece of cake, let's do it. Predict someone's blood pressure from their BMI. We'll use this data set. Then you can do summary. Summary on the fit object gives you lots of good stuff, right? So it gives you the estimated intercept and the slope, right? So the best fitting line predicting blood pressure is 49 plus basically 2/3 times BMI, right? So for every 1 unit increase, BMI goes up, their blood pressure should go up by 2/3 of a point, or a millimeter of mercury or whatever it is. But hey, check it out. So this is telling us there's a standard error, right? Here's your estimated slope for BMI. Here's your standard error. Here's your t-statistic. So the t-statistic is just this divided by this, right? And you can see this goes into that about 6 times. So your t-statistic is big. That p-value is tiny, 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 right? You got the happy stars. We can reject the null hypothesis, right? That true slope is not equal to 0, right? There's a 5% chance we're making an error, but that true slope is not equal to 0. And it gives you other things like your R squared and stuff like that. So you can say, yeah, BMI explains a significant amount of variation in blood pressure, right? for every 1 unit increase in BMI, 0.67 increase in blood pressure, just interpreting that slope. There's simple linear regression, right? This is just telling us that, yeah, we're pretty sure that the true relationship between BMI and blood pressure isn't a flat line, right? We're pretty sure it's we can reject the true slope equals 0, right? We think it's not equal to 0 based on this data. Cool, so that's how you do one in practice, right? And sure enough, right, if you plot this line, right, here's this line, it's got an intercept of 50, it's got a BMI, a slope for BMI of 0.67. So for every 1 unit increase in BMI, you expect blood pressure to go up by 0.67. When BMI equals 0, this line will cross the y-axis at 49, right? But no one has a 0 BMI. The lowest BMI in the data set's 20 or like 19 or 18 or something. And the highest is like, 55 or 60 or something. So it's not, right? It's kind of in this range. Cool. But that's simple linear regression, right? So before we leave, I know it's getting close. I want to do a multiple regression. So hang with me if you want. It'll be recorded regardless. So what else could we use to predict blood pressure? Let's actually look at blood glucose by itself. So we can predict blood pressure from blood glucose, right? And you can see that, hey, it's also significant, right? The slope for blood glucose on blood pressure, we're just running this again. So we're predicting blood pressure from blood glucose, same data set, right? Just a simple linear regression, testing the null hypothesis that the slope is 0, right? We can reject that null hypothesis. Glucose has some association with blood pressure, right? It explains some variability in blood pressure. The slope is small. For every 1 unit increase in blood glucose, predicted blood pressure only goes up by 0.08, right, on average. But it's still significant. And, you could write that up. And there's the relationship there. Notice the slope of this line isn't as steep, right? Cool. So that's glucose's relationship with blood pressure. So far we looked at glucose relationship with blood pressure and BMI relationship with blood pressure, but we looked at them separately, right? What if we want to know, like, hey, for people with a given level of blood glucose, is there still a relationship between blood pressure and BMI, right? So if we only focus on people who have like high blood glucose, do we still see a relationship? We want to hold glucose constant and look to see whether there's a relationship between BMI and blood pressure. So that's where multiple regression comes in, right? We want to predict blood pressure from BMI and blood glucose. And this will be the last example we do today, just because we're short for time. But it's an important example, right? Because you start getting into what it means to control for something. And it's such a huge concept. It's really important, but it's also kind of tedious. Not tedious, it just takes a bit of, like, it takes a while to sink in. So we're modeling blood pressure as an intercept, slope of BMI, plus, or, the BMI times its slope plus glucose times its slope, right? The null hypothesis, and there are going to be 2 of them, right? Because you'll be testing whether this slope is significant and whether this slope is significant. So while controlling for blood glucose, BMI does not explain variation in blood pressure. So once you've accounted for glucose, is there still an association between BMI and blood pressure? That's one of your null hypotheses. For your other null hypotheses, while controlling for BMI, blood glucose does not explain variation in blood pressure. So once you've accounted for BMI, is this one significant? So basically this one corresponds to this one, right? And then this one corresponds to testing this one. And notice, you're saying while controlling for. The model was run with both variables in there, right? This is going to need a picture to really help this sink in. But when you run the model, here's what you get. So this is the way you would actually run that regression. So linear model predicting blood pressure from BMI and glucose, right? And we're using that medical data, and we'll do summary fit. Here it is, right? So there's your intercept. There's your little B1. There's your little B2. Slope for BMI, controlling for glucose, slope for glucose, controlling for BMI, right? But take a look now. Something interesting has happened. This estimate divided by its standard error gives a t statistic that's like smaller than 2 and a p-value that's 0.1. So it's not significant, right? No happy stars. It's not less than 0.05. But BMI is still significant controlling for glucose, right? So weird. So why is BMI significant, but glucose is no longer significant? It's important, right? So And also you can notice things like the R squared went up because we can now explain more of the variation. But focus on this fact that once we've accounted for BMI, glucose no longer explains significant variability in the data, right? BMI is the more important variable. It's accounting for more of that variability. And it was really redundant with glucose. Here's your equation, right? Predicted blood pressure is the intercept plus the slope times someone's BMI plus this slope times someone's glucose, right? If you were to plug in 0 there, the intercept would be the predicted value, which is silly, right? Because no one has a BMI of 0. The slope, though, right, is the slope of BMI on blood pressure holding glucose constant. The other slope is blood pressure, the slope of glucose on blood pressure holding BMI constant. This picture right here it is kind of everything that's going on right now. So we're predicting, and again, this equation right here has 3 variables in it, right? So it's going to be 3 dimensions. You've got this blood pressure variable, you've got the BMI variable, and you've got the glucose variable. If we make a cloud of points, like this right here, we're not talking about the best fitting line anymore. We're talking about the best fitting plane. Like in this cloud of points, what is the best fitting plane through that cloud of points? And so imagine, right? Like it has to make compromises. Oh, I can't see myself. It has to kind of wiggle around, and we're trying to find what those 2 slopes would be. This slope right here and this slope right here, right? This slope right here is what? The effect of BMI on blood pressure, and it's pretty steep. This slope right here is what? The effect of glucose on blood pressure, and it's not as steep, right? So those slopes come from finding that best fitting plane. This is the best fitting plane. It minimizes those little yellow residuals, right? Those are as small as possible with this plane right here. So that plane is given by this equation. So again, it had to take into account both of these variables together simultaneously, right? The best fitting plane is a sort of a compromise between BMI and blood glucose. So what we can do is we can zoom in and just look at this side of the box, right? So we'll just look at the effect of BMI on blood pressure. So this side of the box looks like this. So that's just looking in this side, right? Like glucose goes away, we're just staring into this side of the box. Like put your eyeball right here. Here's what you get if you look in that side. That slope right there is equal to 0.621, right? That's the slope of BMI on blood pressure controlling for blood glucose. This slope right here is looking in the other side of the box. Looking in here, if we put our eyeball over here and look this direction, like look to the left, like in this part of the box, that's the slope. It's much, much weaker, right? The slope is not, like once we've accounted for BMI, the relationship between glucose and blood pressure is no longer very strong, right? We've effectively, BMI and glucose were kind of redundant, right? They kind of, like if you were to look at a scatter plot of them, they tend to go up together, right? But BMI is a stronger signal. And once you've accounted for it, there's nothing really left over for glucose to do, right? There's no longer any variability left for glucose to explain when you've taken into account BMI. But when you take into account glucose, there's still extra variability left over for BMI to explain, right? If you take glucose into account here, there's still variability for BMI to explain. So that's why BMI is significant now, but glucose isn't, even though individually they're both significant, right? That plane has to kind of make compromises and find the best fitting plane, and you can interpret those slopes together. Again, I never saw this presented this way ever. I actually had to kind of think of it myself, but this is my favorite way to like think about controlling, because it's a slope of this plane on this edge. That's one of them. Slope of this plane over here, that's the other, right? And those are literally just your estimates. That one's significant. That one's not significantly different from 0, right? Cool. One last thing before we go. Think about this. Let this sink in, because it is confusing, right? Best fitting plane instead of a best fitting line, right? But whatever, like this, like think about how that plane has to take into account glucose and BMI simultaneously to find the best fit. And then what you're left with is the effect of BMI on glucose. I'm sorry, the effect of BMI on blood pressure and the effect of glucose on blood pressure. And that plane ends up being much steeper for BMI than it is for glucose. So BMI is significant. Glucose isn't really significant anymore. Maybe if you had more data, it would be, right? Because there is a positive, the slope is positive, right? It's just not very big. And relative to the error, relative to the error, it gives you a small p statistic, right? So it's small p-value, or at the big p-value, not less than 0.05. One last thing, and I promise, I know it's spent some time getting set up and I've been blathering, but if you want another way of thinking about controlling, a more like, I want to do controlling myself, I want to like grab onto it and do it. Think about it this way. So what we're going to do is control for the variable manually. So what we're going to do is we'll look at the effect of BMI on blood pressure controlling for glucose, right? So what we'll do is we're going to control for glucose, right? So we're trying to estimate the effect of BMI on blood pressure controlling for glucose. And we're going to do it manually instead of letting, letting the multiple regression do it for us. The way you do this, regress blood pressure on glucose. Find out how much variability in blood pressure you can explain with glucose, and then remove that. What's left over will be your residuals from that model, right? So that's what we're doing right here. We're running a regression predicting blood pressure from glucose. Remember, the residual is the part you can't explain. So we're going to take away the part you can't, or we're going to eliminate the part you can explain and save the part you can't explain. So these residuals are what you can't explain in blood pressure with glucose. So we'll save those. So basically, we're taking out the effect of glucose on blood pressure and seeing what's left in blood pressure. So we'll save that as residual blood pressure once we've taken out glucose. Then we can run this regression, simple linear regression, right? And we're going to remove the effect of glucose on BMI. So we'll remove the overlap of glucose and BMI. So how much of BMI can you explain with glucose? We'll take that away and just leave how much you can't explain. Those are your residuals, right? So we've basically removed the effect of glucose from both blood pressure and from BMI. We've taken glucose out of both of those variables, right? However much it can explain, we've taken it out. And we've saved the residuals, the stuff that's left over. Now, what's really cool is you can take the residual variability in blood pressure and treat that as your response variable, your y-axis variable, and regress it on the residual variation in BMI once you've taken glucose out of both. When you do that, take a look. Your residual, the slope for BMI on blood pressure is now 0.6205. If we go back, 0.6205. That's what this is estimating right here, right? Once you take out the effect of glucose, the estimate is 0.6205. This is telling you, yeah, that's significant. So you can actually manually control for glucose. You can take out how much glucose explains in both of the other variables and then see if a relationship still exists, right? It's really cool, right? And you'll find, sort of as an exercise if you want, I'll just leave you with this for now, you can find the effect of glucose on blood pressure by manually removing BMI from both, right? So just, So just regress BMI on blood pressure, BMI on glucose, and then save what's left over. Once you account for BMI, how much is left over? And then look at that once you've removed BMI and see if there's still a relationship between blood pressure and glucose. It'll be the same number here. That's how you do it manually. Again, this is like, it's stuff that I wanted to see it this way because I didn't like, it's kind of hand wavy, like, oh, you're controlling for it, right? You're like, I didn't know what that meant and it was really frustrating to me. So I wanted to like spend extra time talking about what controlling actually means. So today's been a lot, right? It's nitty gritty about all of these things. But I just want to give you that background, right? Like a lot of this is extra stuff. But think about it, right? It'll make you a better critical thinker. Like this is the reason why this stuff works. And I guarantee you, like, 90% of people who use these techniques don't actually understand this stuff. But you should understand it, right? Because if you don't understand the tool you're using, you're liable to misuse it, right? And that's bad news. So anyway, sorry, God, I keep going over. I don't know. It takes me a while to get set up with this, and sorry about the camera stuff. Notice we still have a lot to talk about, so we'll finish this stuff out next time. It's going to be a lot more focused on application next time. So kind of give you a preview of what's going to happen. We're going to look at dummy coding again, right? We're going to look at how regression is a t-test. We're going to look at how regression is ANOVA. We'll talk about assumptions. We're going to talk about all kinds of stuff. We're going to get into interpreting regression coefficients, right? Especially when you have interactions. And that's going to get, you've done it before, right? But it's hard to do and it takes some practice. So we're going to do all that good stuff next time. So anyway, Oh crap, let me remember where I stopped because I need to know where to cut the slides off. I think it was like 39. Let me just change this up here. I think we can just go like 39, right? No, that ain't right. Oh, well, whatever. You don't need to watch me fuss with the slides. Who's around? Dinge is still there, but you've met Dinge. Y'all want to meet another critter? How many people are still here? 25? A few less than last time. Yeah, sorry. I know y'all got stuff to do and you don't have all day to listen to me talk about stuff that I think is interesting. So I appreciate you humoring me. I promise this stuff is important and understanding it is important. Let's see, who can I grab? Maybe Kiki. Let's see if I can find. You can kind of see back there. Well, let me make this bigger, I guess. I don't know how to, because this isn't Zoom, right? This is just QuickTime, but I guess it's fine. Back there is, that's Kiki's house. This is a smaller friend from last time. How do I do this? This is, let me make this smaller. Maybe not too much smaller. This right here is Kiki, or Kairu. So Kairu is his or her real name. You can't really, so this is a white stumpy tree frog. And he or she is really a good friend, likes a lot of humidity, right? Essentially drinks through their skin and eats lots of mealworms. I actually have like 1,000 mealworms in the fridge because they kind of live in suspended animation when they're in the fridge. Yeah, it's just a white stumpy tree frog, and it's pretty young. It's only like a month or two old, and she's awesome. She's actually being really. Usually she hops around like crazy, but being pretty good. Not very active in the daytime. Does lots of hunting at night. Uh, what else is interesting? They get pretty big. They get to like 4 to 5 inches long. Yeah, I don't know if any of y'all are like reptile-y people, but or like amphibian sort of herpetarium sort of. Because I mean, it's sort of different having a cold-blooded pet, but they're a lot of fun. So anyway, I wonder if I can get her close. That's probably good. And I even have so I was at I can't show you because I'm not on Zoom. I have a Zoom background of her. Anyway, so cool. She's actually gonna just hang out with me, I guess. She likes me because I'm warm. Anyway, all right, y'all. Thanks for putting up with me. I hope everybody's doing okay during all this. Holler at me if you need anything. Yeah, the lab should be pretty straightforward. So don't. You could probably go ahead and start it. I kind of walk you through all the steps. It's not like having to apply a lot of the stuff from lecture, although you will need to apply the inverse of x transpose x times x transpose y, right? That's the magic equation. But that's it. Cool. Is that, how do I think I can't, I think I have to stop sharing the screen. Let me just, how do I quit recording? I quit recording? Oh, was I even record? Oh, okay, good. I'm still recording. All right. Say bye, Kiki. Bye, y'all. Oh, any questions for me before I have to go? I always like try to peace out on y'all before I love the emojis. Uh, any questions? Oh, I need to start up a new discussion board. So all the stuff should be up, but I'll start a new discussion board for this week and it'll have new fun stuff. It was actually really fun talking to y'all about like music and books and stuff. I appreciate the recommendations. Check out, so I made a collaborative playlist on Spotify, but I don't know if anyone's contributed to it. It's just a bunch of my crap right now, so it's probably not of any interest to you. But if you add stuff on the end, like people can skip over my stuff and listen to, you know, better stuff, I guess. All right. Good talking to y'all. I'll see you later. Bye.